In this video, we're going to start topic 9 with our first topic, which is optimization. So this is a pretty simple set of notes as far as what we're going to be doing in terms of the number of things we're going to learn. We're mostly just going to talk about how to solve an optimization problem using a lot of the stuff we talked about in topic 8, specifically extrema. So, just to refresh our memory, in the previous topic, we learned about absolute extrema and local extrema of a function, and we talked about a couple ways that we could find and classify absolute and local extrema. So we talked about using the first and second derivative tests to find and classify local extrema, and we talked about the closed interval test and the global interval method to classify and find absolute extrema. So the question that we didn't really answer with extrema was, why do we care about extrema? What can we do with extreme values for functions? And what we're going to see in this set of notes is the more practical application of those sorts of things, of either local or absolute extrema for functions. So what I mean by more practical applications are things like this. So let's say we have a farmer that has 1,000 feet of fencing and he wants to use it to build a rectangular enclosure. What we will be able to do with extrema, as we'll see in a couple examples, is we might be able to find the dimensions of the rectangle, the length and the width, that would give the closure the maximum area. So maximizing the area. Another example here, say it costs 5 cents per centimeter squared to construct an aluminum can. If a can is constructed to have a certain volume, what are the dimensions of the can, say height and radius, that would minimize the cost, so minimizing a value? Or last example here, say we had a poster board with a certain area and we wanted to print an image on the front. And if we wanted to have a certain margin at the top of the image and then a certain set of margins on the side and bottom, what we could do with extrema is we could find the dimensions of the poster board that would maximize the printed area. So maybe we know we can, say, afford a poster board of this area, and so we want to construct it, or we want to order the poster board so that we can maximize the area of the printed picture. So we see maximizing, we see minimizing. These should sound similar to maxima and minima, these extrema that we were talking about in topic 8. And so what we're going to see is we're going to see how we can use those values to help us answer questions like these. In other words, these sorts of questions where we're optimizing a quantity. So on the next page, I introduce optimization a little bit more formally and, as usual, give some steps here. So problems or situations where we're concerned with minimizing or maximizing a certain quantity are usually referred to as optimization problems. So optimization problem, that title, is a very broad term for a lot of different problems. Usually these are physical problems, not always, but usually they are. And so what we'll be able to see is we'll be able to see, sort of like related rates problems, we often have quote-unquote word problems with optimization problems. They give you some quantities, some variables, and then something that you want to optimize. And so the easiest way, kind of like with related rates as well, the easiest way to understand and get used to optimization problems is to practice with them. So I've got this set of steps here, 5 steps, and what we're going to do as always is we're going to use these steps first by going through this first example here on page 9.1. Or sorry, page 3 of the 9.1 notes. So let's just go ahead and jump right into this example, and I'll go through the steps on the previous page as we talk through this example. So in this example, we have a rectangular field, and we want to basically create the field by constructing a fence on 3 sides and a stream acting as the 4th side of the fenced area or the field. And we have 1,000 feet of fencing. And what we want to do is we want to figure out the dimensions of the fence that will maximize the area of the field. So we've got like this land, and we want to construct these fences in order to pen a rectangular area where one of the sides of that rectangle is bound by this stream. So what's the first thing we should do if we can with an optimization problem? Again, similar to related rates, the first thing we're going to want to do is draw and label a picture and or write down all the information that we know. So that's what I'll do first here on our page. So step 1, I'm going to leave myself some room because there's a lot of stuff we need to do. in a lot of these optimization problems, I'm just going to draw a picture. So let's say I have my stream here, something like that, and I am using that as one side to bound a rectangular area. So just something like this, pretty easy, simple drawing. Help if I could draw a rectangle. That looked good. There we go. So that's the area that we're trying to enclose, and we want to maximize that area. I also know that I have 1,000 feet of fencing, so I'm just going to write that down here. And this is also something that's useful because, as we'll see in the next step, we're going to set up an equation here. It's a good idea to label variables if you can think of the variables that you might need. So this is a rectangular field, so I don't know if the sides are going to be equal or not. So I'm going to label one side length as x and one side length as y. So of course this is also x here, but I'm just going to label one of those lengths as x and the other one as y. So not too elaborate of a picture, just to get a visual of what's going on here. That's going to help us go forward. So that's step one. In step two, we're going to write down a couple functions and a couple equations if we have them. So the first thing we're going to do here in step two is write down what's usually called the objective function. And the objective function is the thing we're trying to optimize. In other words, we're trying to minimize or maximize whatever this objective function is. So if I go down here to my problem and I think about what is my objective function here, what is the thing I'm trying to maximize or minimize, use a little bit of color to help us out. I'm told that I'm trying to maximize the area of this field. Okay. So I want to maximize the area, and I'm going to call that A. And I'm going to give that an equation, so I actually have some quantity that I can maximize here. In other words, if I think about area as an equation, I want to maximize, well, my area is the area of a rectangular segment or a rectangular piece. So the area of a rectangle can be calculated by one side length times the other. So in this case, x times y. So this is the thing I want to maximize. I want to make area A as big as I can. Now, other things that we might need here in step two to help us out are any constraint equations. So these are sometimes, typically things that we run into with physical problems like finding an area or a volume or something like that. And basically with constraint equations, we're stating the restrictions of the problem. Sometimes we might have fewer restrictions, but sometimes we have a lot. It depends on the problem. But it's a good idea to write these down in step two, just so that we know sort of the restrictions, the physical restrictions of our example. Because usually, like related rates, we're dealing with something physical when we're talking about optimizing something. So I'm going to take note of my constraints here, use some more color. So what do I mean by constraints? Well, again, constraints are like what is limiting the problem. What are any restrictions of any particular dimensions or material or values that we might need for this problem. So if we think about this problem for our constraints, we are limited by the fact that we only have 1,000 feet of fencing. So if I had unlimited fencing, I could make this area of this pen as big as I wanted, but because I only have 1,000 feet of fencing, that is acting like a constraint. So my constraint here is I have 1,000 feet of fencing. And the way that I'm going to state that constraint equation is I'm going to state it in terms of the perimeter of this pen. So when I think about 1,000 feet of fencing, what that means in terms of my perimeter, or specifically the perimeter in terms of my fence material, my perimeter is limited to be at maximum 1,000 feet. And I'm assuming I'm not going to want to leave any fencing out because I want to maximize the area, so I want to use all my fencing. So I'm just going to assume instead of something like this, I'm going to assume that I'm going to use all the fence that I have. So what is my perimeter? How can I state my perimeter here? My perimeter is, well, two sides of this penned area are of length x, and then one side in terms of the fence is y. So I want that to be 1,000. So here's the thing I want to maximize, and here I have an equation that involves my constraint, in this case the amount of fencing that I have. All right, so why did I write this out in an equation like this? Why did I care about stating the constraint in terms of an equation with x and y? Well, if I go back to my steps here, in step 3, this is where I use both the objective function and the constraints. Specifically, what I'm going to do is I'm going to use the constraint equation to reduce that objective function to one variable. Now, this isn't always needed. Sometimes we've only got one variable that we're working with in terms of like the amount of material or something. But if we have more than one variable, the constraint equation can be useful to get that objective function in terms of just one variable. So if I go back down here to my steps, notice that my objective function right now has two variables in it, right? It's got x and it's got y. So what I'm going to try to do is I'm going to try to use this constraint equation to get a in terms of either just x or just y. So in step 3, I'm going to solve that constraint equation of 2x plus y equals 1,000 for one of my variables. Now, sometimes one variable might be easier to solve for than the other, or easier to plug into our objective function. Here our objective function is x times y, and our constraint equation is pretty easy as well. So it shouldn't matter in terms of difficulty level whether you solve this for x or for y. In my notes, I have a solve for y, so I'm just going to go ahead and solve this thing for y. So solving this for y means I'm going to subtract 2x from both sides. So I'm going to have y equals 1,000 minus 2x. Now, why am I doing that? Well, if I consider this quantity, now I have y in terms of x. And so what I can do with this is I can substitute this into my objective function for my y, so that the entire objective function is just in terms of x. So this is also part of step 3. So now I'm doing the substitution part where I'm reducing the objective function to a single variable. So I'm going to substitute y equals 1,000 minus 2x into our objective function. So my objective function is up here, a equals x times y. But instead of y, what I'm doing is I'm substituting in y in terms of x. That constraint equation solved for y. So here I'm going to have x times 1,000 minus 2x. And we can see that now my objective function is just in terms of x. So I'm just going to distribute this x here. I get 1,000x minus 2x squared. So this is like my new objective function just in terms of x. So just like we were wanting to originally maximize this, I still want to maximize this. It's just now it's going to be a little bit easier, as we'll see here in a second, because everything is just in terms of x instead of being in terms of both x and y. Okay, now the last thing in step 3 here before we get to the actual calculus part in step 4, I also want to note the domain of my function. In other words, what values can I plug in to my objective function? What are the values that are allowed? So if I go back down here and I note the domain of A, so these are going to be what values of X are allowed, basically, in terms of plugging into this to get a physically possible area. So the thing to note about area, and this is the case with a lot of these physical examples that we're going to be talking about, is we don't want a negative number, right? We can't have negative area. So if I think about this particular example here of A, and even it might help to go back up here and think about A in terms of X times Y, what values of X could I plug in here? Well, I know in terms of my lower value for X, X is also a dimension, right? X is a side length. So I can't have negative side lengths, so X can't be negative. And also, I know that I want this fence to be bounded on 3 sides, meaning that I can't have an X of 0, because if X is 0, I don't have 3 actual physical sides. I'm just going to have a fence that's sitting next to the water, which doesn't make a lot of sense. All my fencing would go to Y. So in terms of the lower value, or the lower limit of X here, X needs to be greater than 0. And again, if I think about what I'm allowed to plug in here for X to get a physically possible area, I also can't have an X greater than, or an X greater than or equal to 500. And this one might be a little less obvious, this 500, but if you consider this piece here of my area function, if X is 500, then my area is 0. And I don't want a 0 area. I want an actual pen with these 4 sides. So I want there to be some non-zero area that I'm enclosing, because I've got this specified, I need there to be 3 sides against this stream. So I need there to be a non-zero area. And the only way that I can guarantee that in terms of X is by, again, taking note of this. If X is 500, I get 1,000 minus 1,000, which is 0. Any X value smaller than that, though, will give me a non-zero area, again, assuming X is also greater than 0. So this is my domain of A. X has to be between 0 and 500. 0 and 500 not included. All right, so that's all stuff we have done that hasn't involved calculus. Step 4 is where we really see the calculus part of this process. And this is where things are going to look somewhat familiar to what we were doing in topic 8. So if I go up here to step 4, this is where we actually do our optimization. This is where we maximize or minimize the objective function using one of those techniques that we talked about back in, or one or more of those techniques we talked about back in topic 8. The first or second derivative test, the closed interval method, or the global interval method. Now, typically when we're dealing with optimization, we're going to want to use one of these 2 methods somehow, the closed interval method or the global interval method, because that's going to guarantee for us that the quantity that we choose for our variable is going to either maximize or minimize the thing we're trying to optimize. So I'm going to want to use one of these 2. And so I need to figure out which one of these is appropriate for what we're working with. So the thing to note about this is I don't have a closed interval, right? This is the same thing as X belonging to 0, 500 with the parentheses, meaning that 0 and 500 are not included. In other words, we don't have a closed interval. This is an open interval. So this is a case where the closed interval method is sort of automatically something we can't do because we don't have a closed interval. We need a closed interval in order to use the closed interval method. So we're going to want to go with the global interval method here. So in order to use the global interval method, let me go back to topic 8 here, and where we were talking about finding extrema. When we talked about the global interval method, The idea is if we are able to find a local extrema, and if there's only one local extrema, then we can automatically say that that local extrema is also a global extrema. In other words, if we find, for example, a local maximum, if there's only one local maximum, we can automatically say by the global interval method that that's also going to be an absolute or a global maximum. So in order to figure out if we have a local maximum or minimum, we have to use those techniques that we talked about to find local extrema. And in the context of optimization, basically what we end up doing is we end up locating any critical points and then apply the first or second derivative test to determine if those critical points are local extrema. So again, for this example, I can't use the closed interval method because I don't have a closed interval for my domain. It's an open interval. But I can use the global interval method. So the first thing I'm going to do here for step 4 is I'm going to find my critical points. So a lot of this is going to be a little bit of a review from topic 8. When I think about my critical points, remember this is where my first derivative of my function is 0. So where is a prime of x equal to 0? And the way that I find that is I take my function, which I'm going to use this version because this version is all in terms of x. I'm going to take that 1,000 minus 2x squared, and I'm going to set it equal to 0 and solve for x. Oh, sorry. I need to take the derivative of that and then set that equal to 0. Sorry about that. So I need the derivative. So if I take the derivative of a, I get a prime of x. Taking the derivative of this, that's going to be 1,000 minus, using the power rule, for x. So this is the thing I'm going to set equal to 0 and solve for x. Sorry about that. So solving for x is going to give me 4x equals 1,000, which means my critical point occurs at x equals 250. So I only have one critical point here, 250, which is a good sign for me because it looks like if I can show that that's a local maximum, I can use the global interval method to say that it's also an absolute maximum. But let's check by the first derivative test to see if this is in fact a local maximum. So by the first derivative test, what I'm going to do is just visualize this. I'm going to draw a little number line here. My critical point is at x equals 250. And so just like we've seen before with the first derivative test, this gives me a couple intervals of values, and I'm going to use those to determine the sign of my first derivative on either side of 250. So I'm going to try to use a prime of, let's do 100. 100 is pretty easy. This is going to be 1,000. Oops, sorry. Yep, 1,000 minus 4 times 100. And remember, I don't really care about the value here. I just care about determining if this is positive or negative. 1,000 minus 400 is positive, so I have a positive first derivative to the left of 250. And for values of x greater than 250, I'm just going to plug in 300. That's not too hard to work with. So plugging 300 into my first derivative, I get 1,000 minus 4 times 300. 4 times 300 is 1,200. 1,000 minus that is, in fact, a negative value. So I have a negative first derivative on that interval. So this is kind of a little bit of a side work here, just making sure that I have a local extrema, and I do. So I can say here by the first derivative test, this value of x, 250, is a local maximum, right? Remember, with local maximum, my slope is increasing, my first derivative is increasing until that point, and then decreasing afterwards. So this is a local maximum. Now I want to make sure this is the actual maximum value of area. So I want to also state that this is a global or absolute maximum. And the way that I can do that is using the global interval method. So if we remember the global interval method from topic 8, we saw that in this last example here. It's the same sort of a thing. We found that there was a single local extrema. And so by the global interval method, we can say that since it is the only critical point and the only local extrema, then that point is also going to be an absolute extrema. So I'll say since x equals 250 is the only critical value, then by the global interval method, x equals 250 is also a global or absolute extrema. More specifically, a global maximum. Okay, so we're almost done. The last and final step that we need to do here is actually state what the question wants us to find. So if I go back up here, that was step 4. That's usually the longest one in terms of work. The last one here is to state the answer to the problem using the correct units. So this last one might seem a little bit obvious as far as what you need to do, but just make sure you're answering exactly what the question wants. Sometimes the question wants the optimized value, so like the maximum area you can attain, or the minimum volume you can attain, or whatever you're trying to maximize or minimize. Sometimes sometimes the problem wants the dimensions that would give you that maximum or minimum. So let's take a look at this question again and see what we want. So we don't actually want the maximized area. We want the dimensions of the fence that will maximize the area. So here in step 5, I'm just going to go ahead and state the values of x and y that would maximize the area. So in step 5, I'm going to say here the dimensions that will maximize the area. Well, I know x is 250. This is in terms of feet. And y, well, I can figure out y based on my constraint equation. Or more specifically or easier, I can use it using that rearranged constraint equation where I solve the constraint equation for y. So I can use this y equals 1000 minus 2x to figure out the length of y. So y is going to be given by 1000 minus 2 times my x of 250, which is 1000 minus 500, or 500 feet. So the dimensions that will maximize the area are x equals 250 and y equals 500. And this is also another reason to draw that picture in step 1, because you know which of these is the one that represents the two sides. So we have two sides of length 250, and then one side, that long side, that's 500. And we can see that from our picture up here. So 250, 250, 500. So that's the idea behind optimization. There's a lot of little steps and some equation rearranging, but the general idea is using calculus to help us maximize or minimize some quantity by using that idea of extrema, what we were talking about back in the topic 8 notes. So let's do a couple more examples. One of these is going to be another physical example. The other one is going to be a little bit less physical and more just talking about an equation. So let's consider this example on page 4. Let's say we have a lidless cardboard box that we want to make out of a flat sheet of cardboard, and this cardboard, the sheet, measures 2 feet by 3 feet. And the way the box is constructed is you cut squares from each corner of this sheet, and then you fold up the sides to make the sides of the box. And what we want to do is we want to find the dimensions of the box that will maximize the box's volume. So again, first thing I'm going to do here is I'm going to write down or draw a picture so that I know physically what's going on in this example. So in this example, I have a sheet of cardboard. And let's say this is the 2-foot side, and this is the 3-foot side. Okay, so now the way that this box is going to be created from this flat sheet is we're going to cut corners out of this sheet. So if I think about just kind of folding this box here, see if I can draw this. Something like this. The way that I would construct my sides is I would cut out these little corner squares, and then I would fold up those 4 side pieces to make the actual sides of the box. So I would have to tape them together. But here's side 1, side 2, side 3, side 4. And if we tape those edges together, that gives us our box without a lid. So just the base of the box plus the sides. So here's my picture. I might add some more to this in a second once I figure out exactly what I need to do here in step 2. So I'm going to go ahead and put step 2 just to the side here, just because this one's going to take a little bit more writing. So step 1 is my picture. Step 2 is where I state my objective function and any constraint equations. So my objective function, remember, is the thing I want to maximize or minimize. So when I consider my objective function here, the thing I want to maximize, in this case, is the box's volume. Sorry, OneNote's frozen on me. Let's see if it'll come back. Hopefully it will. Okay, there we go. So I want to maximize volume, which I'm going to call V. And V, well, how can I state the volume of this box? So with volume, I need 3 dimensions. I need length and width and height for a box shape. So let me just draw those in here so we know which piece is what. Let's say that this is my length. I'll call that L. Let's say this is my width. I'll call that W. And the height is going to be determined by how wide these side pieces are. So for my height, I can think about that as that little height or width of the folded over part. So this width is the width of the base of the box. This height is the width of those pieces that we're folding over, because once they're folded over, that's like the height dimension. So here, when I think about volume, I can think of it in terms of length times width times height. So we have the objective function, the thing we're going to maximize. We also want to write down any constraints we might have. So our constraints are going to be based off of, as we saw in the previous example, the physical limitations of this setup for this problem. So if we look at this box, we can think about a couple possible physical limitations for the dimensions themselves. So I'm going to start with the length. So length is based off of this dimension here, and we can see that the maximum size for the length is 3 feet, right? So if we think about a box with no sides, the length is at maximum 3. But we probably want some sides to this box. We actually want a box instead of the sheet. So in terms of what I'm subtracting from this maximum value of 3 feet, I have 2 side pieces, and both of these side pieces are of width or height h. So for my length, the way that I can think about the constraint for length is it's going to be 3 minus 2h. So 3 minus 2 of these side pieces with height h. Same idea for my width. Width is at maximum 2 feet, so if I don't have any h, no height, just a flat surface, my width is going to be at maximum 2. But I'm hoping I'm going to have some sides to this box, and just like for the length, where we had 2h taken out of that maximum quantity, it's the same for the width. Here's one side, here's another side. These should both have a height of h, so my constraint for width is 2 minus 2h. Now, the reason I'm phrasing both of these constraint equations in terms of h is because, again, what I want to do in step 3 is I want to use the constraints to rewrite my objective function in terms of just one variable. And so now here in step 3, the way that I've written these constraint equations is I can actually now write my entire volume equation in terms of h, my one variable. So just to remind us, step 3 here. This is where we use the constraint equation or set of equations to reduce the objective function to one variable. This is especially useful here because we're actually starting with 3 variables, right? Length and width and height. But what I can do now, based on these constraints, is I can rewrite the volume in terms of just height. So volume was originally length times width times height. I just said length could be written as this, 3 minus 2h. Width could be written like this, 2 minus 2h. And then height is still just height. So I can rewrite that whole volume equation just in terms of h. And as usual, I'm going to need to do some stuff with this volume equation. Particularly, I'm going to have to take its derivative. So I'm going to make life a little bit easier, and I'm going to expand this out. So multiply through all those pieces, FOIL these, and then multiply them by h, by this h. And that's going to give me a volume equation of 4h cubed minus 10h squared plus 6h. So this is now my new objective function. It means the same thing. It's still the volume, but now it's just in terms of h. Now, just like we did in the previous example, I also want to state the domain of my function. So that's also part of step 3. So this is the domain of v, and my variable here is not x, I'm calling it h for height. So this is like my volume equation in terms of h. And if I think of my domain here, well, what values could h possibly be? Well, the smallest that h can be is 0. I'm not saying anywhere in this question that I have to have a volume that's at least greater than a volume that's greater than 0. I just want to maximize the volume. So technically I could have a value of h that's 0. It would just mean I would have no volume, and that we'll make sense of that in just a second. And in terms of the maximum value of h, so if h is 0, then I'm going to have a volume of 0 because I'm not even going to have an h dimension. But in terms of a maximum volume of h, it helps to look again at these constraints. So volume and width and height and length, these are all physical measurements that can't be negative. And so if I think about my width constraint here, I don't want a negative width. So that means that h can't be greater than 1. Because if h is greater than 1, then I get a negative width. If h is 1, I get a 0 width, which just means that, once again, I'm going to have a volumeless box because it's not even going to be a box. But in terms of these physical measurements like width, h has to be at maximum 1, because if it's anything greater than 1, w, width, goes negative. If h is 1, length is still a positive quantity, that's fine. But w is the one that's restricting the domain here, in the sense that the maximum h can be is 1 in order for all of our 3 dimensions, length, width, and height, to all be positive or greater than or equal to 0. So here's our domain. Okay, so there's step 3. Now in step 4, this is again where we do some calculus. This is where we actually minimize or maximize the quantity that we want using one of these techniques that we talked about back in topic 8. Now, one thing that's a little bit different in this example than the previous is we do have a closed interval for our domain. And what that allows us to do is it allows us to use the closed interval method. So remember the closed interval method. If I go back here to topic 8, the closed interval method here on page 6 is where we list all critical values, singular values, and endpoints. And then we just figure out which of these values gives us the largest value of our function. That gives us the global or absolute maximum. And whichever value gives us the smallest value of our function, that gives us our absolute or global minimum. So to start using the closed interval method, I'm going to go ahead and list my critical values, singular values, and endpoints, and then use those to figure out which of those values maximize volume. So let's start with critical points. So critical points are where my volume, the derivative, is equal to 0. So here's my objective function in terms of h. So if I take the derivative of that, that's going to be using the power rule here, 12h squared minus 20h plus 6. And I'm going to take that 12h squared minus 20h plus 6. I'm going to set it equal to 0, and I'm going to solve for x. Now this is a case where I don't have a really nice factorable expression here. It's not easy for me to factor this. So what I'm going to do is I'm going to use the sorry for the pause, my cat was jumping on things. I'm going to use the quadratic formula to solve for x here. So just a reminder about the quadratic formula. That is given as negative b plus or minus the square root of b squared minus 4ac over 2a. So if you can't factor this easily, you can always use the quadratic formula. We're going to get a decimal or set of decimal answers here, but we can use that. So if I use my quadratic formula here, I'm going to get negative b, so positive 20, plus or minus the square root of negative 20 squared minus 4 times a times c, all divided by 2 times a. That's going to give me 20 plus or minus the square root of 112 over 24. And that's going to give me two values of h. H is either 1.2743, I'm rounding here a little bit, or h is 0.3924. Now I get two values of h, but if I remember the domain for this particular physical example, h has to be between 0 and 1, 0 and 1 included. So I can actually exclude this value. Because for this example, the physical constraints of this example, h has to be between 0 and 1. So I can exclude that value of h that's greater than 1. So this is my critical value, or the critical value that physically works with this example. So that takes care of my critical points. What about singular points? So remember, singular points occur where my first derivative is undefined. Well, my first derivative is a polynomial, which is defined for all values of x, so I don't have any singular points. So I'm going to say here, my first derivative is defined for all values of x, which implies no singular points. So critical points, singular points, the last thing I need here to use the closed interval method are my endpoints. These are usually the easiest ones to write down because these are the endpoints of our closed interval. Which means, if I go back up to my domain, my endpoints of this interval are 0 and 1. So h equals 0 and h equals 1. Okay, so it looks like I have three values to check for my global extrema, my global maximum in this case. This critical point here, and these two endpoints. So remember how we did this back in topic 8. So on this example here on page 6, we were basically doing this same thing. We listed the critical values, singular values, and endpoints for this example on page 6, and then we made this little table where I said, here are the values of x that I'm checking, here's the function value at those x's, and whichever one gave me the largest function value, that ended up being my absolute or global maximum. And that's what we're going to want to look for here because we're trying to maximize volume. So I'm going to go ahead and start by making my little table here. My values of x, and my volume evaluated at those values of x. So my values are 0, move this over here a little bit, 0.3924, and 1. So again, with this method, I'm not plugging in my values to my derivative, not here. I'm plugging these values into my volume equation. So just to write that volume equation down here, this was 4h cubed minus 10h squared plus 6h. So at 0, I get 4 times 0 cubed minus 10 times 0 squared plus 6 times 0. That gives me 0. The volume at 0.3924, just for the sake of space, I'm not going to write that in here, but it's the same thing. I'm just plugging in 0.3924 into each of my h's, and that's going to give me a volume of 1.0563. And then for volume at 1, same thing. I would plug in a 1 every place I see an H, and I would once again get 0. So this looks like it's my maximized volume. So I can say here at the bottom, by the closed interval method, volume at an H value of 0.3924 gives me a volume of 1.0563, and this is in terms of feet cubed, is the maximum volume. Now in step 5, I'm going to put that over here. Remember this last step just to make sure you are writing down exactly what the question is asking for. So in step 5, I want to make sure I'm stating what we need. So I don't really care about the maximum volume. I want the dimensions of the box that give me that. So in step 5, I'm just going to make sure I write down those dimensions because that's exactly what the question is asking for. So I'm going to say here the dimensions that maximize volume are H, well, we just figured that out. That was that 0.3924. That was the critical value. And that's in terms of feet. The other two dimensions that we have to worry about are length and width. So length, how do I figure out length? Well, I can go back to those constraint equations. Length is 3 minus 2h. So 3 minus 2 times 0.3924. That's going to give me 2.2152 feet. And width, again going back to those constraints, that was 2 minus 2h. So my maximizing value of width is 2 minus 2 times 0.3924, which gives me 1.2152 feet. And so specifically, these are the values this question is asking for, the values of the dimensions of the box that maximize the volume of the box. And if we just take a quick second, note these other two values that we got from this table, this 0 here and this 0 here. These make sense for the volume to be 0 when the height is 0 and the height is 1. Because if the height is 0, go back up to our picture, we just have the flat cardboard, right? We just have length times width. There's no volume. It's just a flat piece of cardboard, so volume is 0. Same thing when h was 1. We said when h was 1, width is 0, because that basically means we're just cutting cutting this box in half here for the two sides, so we don't again have a volume to speak of. So when h hits its maximum in its domain, just like when it hits its minimum, the volume doesn't even exist. We don't have 3 dimensions, so volume is also 0 there. All right, let's do one more example here. And this one's less of a physical example and more of one where there's not really anything to write or draw. It's more of just kind of going right into step 2. So this one is more to show that you can still do optimization problems when it's less of a physical or drawable problem. So here we have two numbers, x and y, such that x is greater than or equal to 0 and x minus y equals 4. And we want to figure out how small we can make this quantity, x squared plus 2y squared. So there's not really any picture here that I can draw, not really a step 1 that I can do. So I'm just going to go ahead and jump right into step 2. So step 2 is where we list our objective function and any constraints. Okay, let's start with our objective function. All right, what am I trying to minimize and maximize in this case? I want to see how small we can make this x squared plus 2y squared. So this is like my objective function. I want to minimize. And I'm going to call this thing a function of x, even though there's a y in there. As we'll see in a second, we're going to get rid of that y with the constraints. So I want to minimize this function of x squared plus 2y squared. And when it comes to constraints, these are more about the specific values of x and y. So x has to be greater than or equal to 0, and x minus y has to be equal to 4. So x is greater than or equal to 0, and x minus y has to be equal to 4. Now, like I just mentioned, in step 2, I wrote my objective function as if it was already a function of x. I said f of x equals this thing. In step 3, what I'm going to do is I'm going to use my constraints, or more specifically one of my constraints, to get this actually in terms of just plain old x. So it is a function of x. So remember step 3, this is where we put together the information from our constraint equation to reduce the objective function to one variable. So right now it's in terms of both x and y. I want to get it in terms of x. You could also try getting it in terms of y if you wanted to. X is usually the default variable, so I usually stick with that if I have to solve something to be expressed as a single variable. So in step 3, I'm going to solve this constraint, x minus y equals 4, for y. So this was one of my constraints. And if I solve this thing for y, I'm going to end up getting y equals x minus 4. And so now what I'm going to do is I'm going to substitute that in for my y in my objective function. So substitute y equals x minus 4 into our objective function. So now this objective function is actually going to be a function of x. It's going to be x squared plus 2 times y squared. So y is x minus 4. And if I wanted to, I could expand this out, but this isn't too bad to take the derivative of. I'm going to have to do that in a second, so I'm just going to leave it as it is. And I know from my constraints, if I think about the domain of f of x, I know that x has to be greater than or equal to 0 based on this. All right, now, as far as step 4 goes, where we actually do some calculus, try to maximize or minimize a quantity, I want to look at the domain of my function. This is not a closed interval, so I'm not going to be able to use the closed interval method. I'm going to want to use the global interval method, or the global interval method like we did up in this first example. So what I'm going to do in order to use the global interval method is I'm going to start by finding my critical points, and then I'm going to use that first derivative test to determine if I have a critical, or if my critical point is a local minimum or maximum. So here in step 4, I'm going to start with my critical points. So where is f prime of x equal to 0? Well, let's first find f prime of x. So let's find that first derivative. So I'm taking the derivative of this. So derivative of x squared is 2x plus derivative of this piece. It looks like I can use the chain rule. I have 2 times that exponent of 2, so 2 times 2 is 4, times x minus 4, that's going to be raised to the 2 minus 1 using that power rule. And I'm going to multiply that by the derivative of my inner function here, the x minus 4. Derivative of that is just 1. So I get 2x plus 4 times x minus 4, which is 2x plus 4x minus 16, or 6x minus 16. So this is my first derivative. And as usual, to find my critical points, I'm going to take that first derivative of 6x minus 16, set it equal to 0, and solve for x. That gives me 6x equals 16, or solving for x, I get x equals 16 over 6, or 8/3. So this is my critical point here. All right, now let's do the first derivative test. So I found a critical point. There's only one. So now let's see if that is a local extrema, and if it is, if it's a local maximum or a local minimum. So I'll put my number line up here. Here's my number line. There's 8/3. And once again, it looks like I have 2 intervals to check the sign of my derivative. So for values of x less than 8/3, I'm going to plug in a value of 0 into my first derivative. So 0 is on this side of 8/3. Let me scroll up here so we can see our first derivative. It's just 6x minus 16. So this becomes 6 times 0 minus 16, which is a negative value. So 0 minus 16 is negative, so on that interval my first derivative is negative. On the interval for x greater than 8/3, this interval, I'm going to plug in a value of 3. So I get 6 times 3 minus 16. 6 times 3 is 18, minus 6 gives me, or sorry, minus 16 gives me a positive first derivative. So I can see that my first derivative is switching from negative to positive as I cross 8/3, which means that that 8/3 is a local minimum. So if you go back and look at the first derivative test information, way back here in topic 8.2, we said that if our first derivative changes from a negative to a positive across a critical value, that critical value is a local minimum. So I'm going to say here, by the first derivative test, x equals 8/3 is a local minimum. Now again, I don't have a closed interval here. I have just x has to be greater than or equal to 0 here for my domain. So what I'm going to want to use here for my final conclusion is the global interval method. So if I scroll back up to that first example here where I said, since x was the only critical value, then we can say that it's also a local maximum. It's the same thing here. Since x is the only critical value in our case, then by the global interval method, it's also going to be a global minimum. So I'll say here, since x equals 8/3 is the only critical value or critical point, I can say then by the global interval method, x equals 8/3 is also a global minimum. Okay, so we found the value of x that is a global minimum. So in step 5, as we've seen in the previous two examples, I want to make sure I'm actually answering what the question wants me to state. So let's go back up and check what we want here. So go back up to our question. How small can we make x squared plus 2 times y squared? So in other words, what I want here is I want that value. What is the smallest quantity of this thing? So the smallest value of x squared plus 2y squared is, okay, well, x we just said was 8/3. So this is going to be f of 8/3. X squared is 8/3 squared plus 2 times y squared. Y we set up here was x minus 4. So that's going to be 8/3 minus 4 quantity squared. And if we calculate that out, we're going to get 96/9, which is 32/3. You can leave it like that, or if you want what this is approximately as a decimal, we get 10.6667. So 32/3 or decimal approximately 10.6667 is the smallest value of x squared plus 2 times y squared given these constraints. X has to be positive and x minus y has to be 4.